In this video, we're going to talk about recursive processing of arrays. Recall in computer science, recursion is a method of solving a problem where the solution depends on solutions to small instances of the same approach. This problem-solving technique could be applied to solutions involving arrays, namely in reordering of the data inside the array, or sometimes in sorting information in the array. So we can use recursions for this kind of stuff. So let's take a look at a specific example. So this example is what we call binary search. And this solutioning applies to array of data that have been sorted already. And we're going to delve into the details of the implementation as we go through this. Let's talk about binary search. So binary means two. So every time when you are doing a binary something, this approach involves dividing and conquering your search problems, splitting up into two. If you do this multiple times, if you have n number of variation as your inputs, your binary search is going to cut the control plane, the space from this big into two portions. This division calls for O of log n. So this is a very efficient mechanism for solving this type of problem. The problem is finding a target elements in the sorted array. So if you have an array of n number of elements, so this is index 0, 1, 2, all the way through n number of them, ARR right here. Sorted arrays means that all of the information in there are in some sort of order, either in the ascending order or descending order. As I just said, we have all of the elements in there in the ascending order, meaning they're going up, like -1, 0, 9, 13, 14, 32, so on and so forth. The problem here is defining a target element. So this target element in the context of an integral array is a number. So this could be 20. Finding a 20 inside this array. We can just use the brute force methods, right? Looking into array index 0, 1, 2, 3, 4, and just keep going until you find 20. And this will guarantee a solution because this is a sorted array. So at some point, you're going to get what you need. Sequential means O of n. Since we're talking about recursion, we can use a recursive technique to recursively repeat this approach of looking into cutting a control plane in half in O of log n fashion to find the targets that you want. So let's look at the specifics. Assuming that we have an array of 8 elements in there and the targets that we're looking for is number 20. This is the integer array. So what we need to do is to have a two-pointer approach. When I say pointer, I mean indices. The other pointer is called last. So you have a two-pointer approach. You would continue your iteration, or at least your base condition is such that if first is always less than last, then you want to continue your iteration. Now your target is 20. Regardless whether 20 exists, you want to be able to cut your problems in half using the recursions to see if this value does exist or not. Okay, so let's take a look at the specific mechanisms. After declaring your initial pointers, your first is assigned index 0 and your last is ARR, this array name is ARR, dot length -1. If you have 8 n number of elements and your very last index is 7, that's ARR dot length -1. Every array is an object at runtime in Java. The first thing that you want to compute is midpoint, which is first plus last divided by 2. This is very interesting. We've got first being 0, last being 7. So first is 0, last is 7. If you do a computation, 7 divided by 2, this should give you a 3.5. But when you do a division, what you're getting is the quotient, and that should give you a 3. This is an integer. Instead of getting a 3.5, you basically have to write a method or function to do that work. You don't here in this case. If midpoint is integer and you get some sort of division, your precision goes into the nearest integer without rounding. Once you find out what the midpoint index is, you basically get a value out of it, and you see this value is greater than or less than the target. Depends on whether your target lands on the left side or the right side. And you can continue the same approach by resetting your first or resetting your last. Continue the same search mechanisms in place. So that's step number 2. And let's move on. So now that you know where your midpoint is and you know where your target is, if your midpoint is first plus last divided by 2. If this midpoint is less than target, this means that target is actually on the right side of your midpoint because everything is sorted, right, in the ascending order. Then you know the control plane that you need to look for is from here to here. If midpoint is less than target, then you know the control plane is actually on the left side. Your midpoint is pointing to 15. In the prior iterations, target was 20, midpoint was 15. So this sets our new control plane to first equals 4. First has to be on the 4th index when you start a new search again. But your last hasn't changed. You eliminated half of the control plane. You set up with the right side. That's the third iteration. You just continue the process. Given your first is 4, last is 7, your midpoint is 4 plus 7. This actually gives you 5.5 because we're only taking the nearest integer without rounding. 20 is less than 22, meaning target less than midpoint. The new midpoint we're talking about. Let's move on to the next page. This fourth iteration says, I've just eliminated this. So the answer is not here. There's nothing here to look at. And I've also eliminated this because the midpoint for the second iteration shows that the midpoint is 22, but your target is 20. So the answer's got to be here. And it turns out that first and last, they both converge at index 4, and that gives you a value of 20. And then we turn true. So you guys can see the patterns here. The question is, what if we don't have 20, but 18? Then again, going through the certain set of iterations, we're going to land on 18. 18 replacing 20 as the fifth element. What do you do if target is not in the array at all? Let's just say the target is 19. You have completely eliminated every single element of it. If first is less than last, or you can say while, and they just keep going until first completely crosses over last. If at that point your target still hasn't been found, you return false from there. Let's look at how this is implemented. The logic is very simple. First of all, you start up with a recursive function, or if this is part of your class, this would be a method, not a function, which returns a Boolean. And this one has your target, the value that you're looking for, or needle in a haystack. And then you have your first and last. So we know first is always 0, and last is whatever the array dot length minus 1, because array indexing starts with 0. This is your base condition. Base condition is your exit strategy. You don't want to keep this recursion going. When first becomes greater than last, that means the pointers crosses each other and you return false right away. Every recursion has to have a base condition. If this is not a base condition, what you have is a divide and conquer. This is your new first. When target is greater than value, you know that the target is actually on the right side of your array. Assuming this is the array, right side of the midpoint, this is midpoint. This is your midpoint plus 1. That's your new first, the new first. Last is still here, and then you can search on this plane. If target is less than or equal to value, then the target that you're trying to find, it's got to be on the right side. So this is your midpoint, and your control plane is still the first 0, but your new last is midpoint minus 1, right? This is midpoint minus 1. So this is your new first and new last when you begin this recursive call. So this binary search itself is what we call a recursive function. So what we see here is divide and conquer. Problem is getting smaller and smaller. That's condition number 2. The first condition is base condition. The second condition is smaller problem. The third one is generalization of the whole thing. Everything could be expressed in terms of variables. There is no hard coding. So you can generalizing this entire representation into this formulation. This also qualifies the generalization criteria. Recursion satisfies the 3 asks. The first one, base condition. The second one, smaller problem. The third one, generalization. So this is a quick illustration of how recursion works in the context of binary search using array.